Hello, chemists. We are going to continue our journey in understanding bonding. We're getting into an intermediate step and we're talking about something called the Lewis structure. And that Lewis structure is really important in just figuring out how atoms are attached to each other. Once we do that, we're going to get into three-dimensional shapes. And so we're going to proceed forward and just talk about Lewis structure for a compound, and I'm going to give you the protocol, the rules for that, and give you some examples of that. And then we'll have our next video on how do we put those objects into three-dimensional space. Okay, so we're starting here on number 8. The Lewis structure for a compound. Basically, the only thing this is really good for is determining how atoms are attached. Determining how atoms are attached to each other. Okay, and I'm going to just basically skip over into another page and give you just a protocol for that process. So I'm going to go over here to a blank page and I'm going to just proceed. So for doing the Lewis structure for particles, okay, and I'm going to go ahead and do water as we go. Okay, so the first thing we have to determine is the number of electrons involved in bonding. And what we've done is we've learned about valence electrons. So you basically are just going to add those electrons up so that we can put them in and have them bond with each other. So basically, when I look at water, I know that there are 2 hydrogens, and each of the hydrogens have 1 valence electron. There is 1 oxygen, and that 1 oxygen has 6 valence electrons. And when I add those up, there are 8 electrons, and these are the electrons involved in bonding. So we talked about those valence electrons for a purpose, and now we're using those. Okay, so we're going to calculate the number of electrons involved in bonding. So basically a calculation there, all right? So for water, we've done that. For the second thing we're going to do is we're going to determine what we're going to call the central atom. The central atom is obviously the atom in the middle. Now, quickly, we're going to ramp this up into big molecules like those macronutrients or biomolecules that we speak about. But the crux of the matter is it just comes back to what those atoms are immediately attached to. So the trick to this is the central atom is always going to be the atom that makes the most bonds. And we talked about knowing valence electrons and the number of bonds so that we could do this, the most bonds. So basically, for our purposes, carbon is always going to be central because it makes 4 bonds, right? We talked about that. Hydrogen and halogens are always going to be peripheral, I forget how to say it. On the outside. Let's do that. Peripheral, I can't spell it. But on the outside, so just write outside. Okay, and that's because they only make 1 bond, so they're never going to be in the middle. They never make more than 1 bond. Okay, so and this is a very hard step, so this is the hard part. I think this is really hard to determine. So just keep that in mind, that is difficult to determine, and often there'll be more than 1 central atom. But for this really simple element, or this really simple compound, water, we know that oxygen makes 2 bonds and hydrogen makes 1, so we're going to put oxygen in the middle. And then we're just going to surround it symmetrically. So basically, we're surrounding the central atom symmetrically with symmetry, okay, with the other atoms. And that's tricky, but basically, you'll figure it out as you practice. Okay, third step. So we've got determining the central atom as our second step. Our third step is to connect all atoms with 2 electrons. Okay, so you're going to use up your valence electrons up here, the ones that you calculated up here. You're going to use them to connect them. And I'll just say that 1 bond, a single bond, is 2 electrons. A double bond, we'll do it like this, a double bond is equal to 4 electrons. And you can have a triple bond, and that's equal to 6 electrons. Okay, so that will happen. We'll talk about it later, but it will come back to us. Okay, So essentially what I'm doing here is I'm taking my, my hydrogen, oxygen, and I'm using up 4 electrons right here to connect them. So what I've done now is from my 8 electrons, I've used up 4 electrons to bond. Okay, so here's where I am at this step. I've connected all the bonds with 2 electrons. Okay, so the fourth thing we're going to do is we are going to go back now and provide octets. Okay, and remember octets, those are the 8 electrons that everybody's trying to achieve, with a couple of exceptions to atoms that require an octet. Okay, so we know oxygen requires an octet, and so basically we've used up 4 of the electrons to bond, so we have 4 electrons left. So what we're going to do is we're going to go and put those electrons, hydrogen doesn't want them, so I'm going to put them on oxygen, and what happens here is by this covalent structure, by sharing, hydrogen is getting 2 electrons, which is what it wants. This hydrogen is getting the same, and this oxygen, by sharing, is getting 8 electrons, which gives it its octet. It might be helpful to see that, that electron came from, but it's being shared by, but it came from the hydrogen, and that electron too. But those electrons are now being shared so that everybody gets what they need, which is stability. Okay? So that's when everything goes well. That's cool. That works well. So there are some additional steps that are important. Number 5 would be, so sometimes it doesn't work, and so you have to move electrons to create double or triple bonds. Double or triple bonds. So that sometimes happens. There are some weird ones, anomalies, okay? The other thing that I'll say is if you have an ion, okay, we talked about cations and we talked about anions, all right? If you have a cation, when you add, so when you do step number 1, when you determine the number of electrons, okay, you have to subtract electrons equivalent to the charge. Okay, so for instance, one of the common substances that we use, this is ammonium. It is a polyatomic ion that we'll talk a little bit about later. When I determine the number of electrons for this substance, I know there's 1 nitrogen, so there's 1 times 5 because it has 5 valence electrons. There's 4 hydrogen, so there's going to be 4 times 1 for a total of 9 electrons. But because of this positive charge right here, I'm going to subtract 1 electron. Oops. I don't like that. That says 11 instead. Okay, 1 electron for the charge, right? And so I have 8 electrons. One of the things that I'll say is that you're never ever going to have an odd number of electrons. So you know something's up here. Whenever you're doing Lewis structures, you're always going to end up with even. So you always want to have an even number of electrons once you play this game. That's a really big deal. Okay. Another substance that you'll be familiar with is an anion. I'll get to that in a second. I'm ahead of myself here. On this one, when you determine the number of electrons, right, you're going to add electrons equivalent to the charge. Because basically anions are negative and they need extra electrons. So that substance I was just talking about is called phosphate. It is one of the pieces of the backbone of DNA that you'll learn about. So it's a really important particle. When I add up the electrons that are involved in this process, I have 1 phosphorus that is 5. So there's 5 valence electrons in phosphorus. There are 4 oxygens, which means there are 4 times 6 valence electrons for oxygen. I'm just double checking that I did phosphorus right. I did. And then, so we get a total of 4 times 6 is 24 plus 5 makes 29 electrons. So then you go, wait, that's an odd number. That doesn't make sense. So again, what we're doing is we're looking at that charge right there. And so we're going to add 3 electrons equivalent to the charge to get a total of 32 electrons that will be involved in the bonding process for phosphate. Okay, so that's kind of all that I needed to show you at this point. What I've done on subsequent pages here is I have done those Lewis dot structures for several different substances so that you can see them, and I've tried to annotate what's going on there. So hopefully that will help you a little bit so you can kind of see those are completed for you. And there's another page right here. So ultimately what happens here is there's lots of practice problems that I've completed for you, and I encourage you to look at those and come to class with some questions, okay? We will pick up on the next video right here where we take what we've learned with Lewis structures and go into the three-dimensional shape, okay? So molecules are three-dimensional and we need to be able to see them as such. And so that's where we're going next. I hope you're having a great day. Thank you so much for listening.